So question 9 of 3.1, if a set A has 63 proper subsets, then what is the cardinality of A? Well, if it has 63 proper subsets, so this is testing a bunch of definitions, right? You don't know what a subset is, but you also don't have to know what a proper subset is. A proper subset is just a subset that is not the entire set itself. So this is answering Max's earlier question. Every set is a subset of itself. A is a subset of A. Okay. So if there are 63 proper subsets, how many subsets are there? Well, 64. All of them, all the 63 there, plus the one more that is the set itself. So if there are 64 subsets, then what's the cardinality of A? Well, you're doing a counting problem here in reverse. And you're asking the question, how many elements or how many different subsets are there of a set? And the way to do that counting problem is you line up the elements of A beginning to end, and you say, okay, the first one, is it in the subset? Yes or no? 2 options. Second one, is it in the subset? Yes or no? 2 options. Third one, is it in the subset? Yes or no? 2 options. And so you get 2 times 2 times 2 times 2 times 2 all the way down to the power of n. So if there are n elements in the set, then the number of subsets is 2 to the n. Here you've got 64 subsets. All right, well, 64. So 3 is 8, 4 is 16, 5 is 32, 6 is 64. So 2 to the power of 6 is 64. So that tells you that my set A has 6 elements in it. Okay, that's part A. Part B, if a set has 64 subsets of odd cardinality, what is the cardinality of B? So odd cardinality, okay, so what does it mean to be odd cardinality? I mean, the cardinality is the number of elements in the set. So odd cardinality, an odd number of elements in the set. All right, so if it has 64 subsets of odd cardinality, what could B be? Well, what we're doing here is we're counting subsets that are of odd cardinality. So what the process I just described, which is, is the first element in, yes or no, is the second element in, yes or no, that counting way won't work for this kind of situation. But what will work is, let's write that out. Let me share the document camera here. Okay, so the point is that every subset of A has a certain number of elements, right? So how many subsets of A have 0 elements? Yeah, Sam's right, 1. What is the number of subsets of A with, I guess I should say cardinality, 1? Well, let's in this example, I'm just saying A is a general set, not telling you how many elements there are. And let's say it just has n elements. How many subsets of A have cardinality 1? Well, n, yeah. You're taking, if there's n elements, you've got 1, 2, 3, 4, 5, all the way to n. Well, then there's the set containing 1. There's the set containing 2. There's the set containing 3. There's the set containing 4, and so on, right? You can just do every one element. Then you get into the number of subsets with cardinality 2. How many are there? Another way to ask this question is, how many different ways from a set of n elements could I choose 2? n choose 2. And now all of a sudden, you see the pattern. Because this was n choose 1. This was n choose 0. And so if we repeat this pattern all the way down, cardinality 3 is n choose 3, cardinality 4 is n choose 4, and that makes sense. How many subsets have cardinality 4? Well, it's the number of ways to choose 4 elements from the set. That's exactly n choose 4. And you repeat this all the way down to the number of sets with cardinality n, which of course is 1, the entire set itself, which is n choose n. How many ways can you choose how many ways can you choose n elements from n elements? Well, there's only one way, choose them all. All right, well, if I add up everything on this list, what do I get? Number of subsets of cardinality 0, number of subsets of cardinality 1, number of subsets of cardinality 2, all the way down, number of subsets of cardinality n. The rule of sum tells me that what I'm doing here is adding up all the subsets. Right? The left-hand side is just the number of subsets. The right-hand side, what have I got? N choose 0 plus n choose 1 plus n choose 2 plus n choose 2 all the way up to n choose n. So I've got a sum. N choose I as I goes from 0 to n. Now, anybody see a way we can simplify that? Yeah, binomial theorem, absolutely. Remember what the binomial theorem says? It says take for any x and y you want, and for any n positive integer, or 0, I guess, x plus y to the power of n is the sum of n choose I, x to the I, y to the n minus I, where I goes from 0 to n. Okay, so how do I make this apply to this? Well, this is the sum of n choose I, and I've got that, the sum of n choose I. What do x and y need to be so that here they're gone? 1 and 1, exactly. If I make x 1, then I get 1 to the power of I, which is just 1. If I make y 1, then I get 1 to the power of n minus I, which is, again, 1. So n choose I times 1 times 1. Oh, those are just gone. So what does the binomial theorem say when x and y are both 1? 1 plus 1 to the n is equal to the sum as I goes from 0 to n of n choose I. Oh, what's 1 plus 1 to the n? That's 2 to the n. You see, this is where everything comes full circle. 2 to the n is exactly what we counted earlier as the number of subsets. Okay, so what this gives us is another way to count the number of subsets of a set. The number of subsets of any set is 2 to the power of the cardinality of the set, and that's equal to the sum of n choose I, where I goes from 0 to n, by the binomial theorem. Okay? Now the question was, if B has 64 subsets of odd cardinality, what's the cardinality of B? Now here's the interesting thing. I'm going to take the binomial theorem and apply it in a slightly different way. Hey everybody, let's take a break from the example for a sec. The example I'm doing here is really just a single example, and there are literally infinitely more problems you can run into on a discrete math exam. And odds are good you'll run into problems you've never seen before and be expected to apply what you know to solving them. But if you don't understand the content, you have no hope. So if you're taking a university, if you're a student taking a university discrete math course, and you're serious about not just getting a good grade, of course, yes, getting a good grade, but if you're serious about understanding the content, then go ahead and click the first link in the description down below and book a free call with me. Now, back to the example. Paper here. Watch what happens if I take x is 1 and y is -1. Yeah, what's that going to do? What do I have on the left? Actually, I'm going to put, I'll write that slightly differently. -1 + 1. Doesn't change much. Doesn't change anything over there. I'm just going to put the negative inside the x here, just to make the numbers easier to use. Okay. So on the left, what do we have? Don't worry, this is very relevant. Yeah, Gherkin got it. The left-hand side is 0. What do I have on the right? Well, I got +1 to the power of n minus I. So that's just gone. That's just 1 all the time. But the -1 over here, -1 to the I, when I is 0, it's positive. When I is 1, it's negative. When I is 2, it's positive. When I is 3, it's negative. So it's repeating, right? Positive, negative, positive, negative. And so what we get is 0 on the left is n choose 0 minus n choose 1 plus n choose 2 minus n choose 3, and so on. And then I guess it would be plus or minus n choose n, the last one, depending on whether n was even or odd. Okay. Everybody good with that so far? That's a 1.3 problem there. Any questions on that? I'm going to apply it to this situation first, or right away, but before I do, any questions on that? No, it's good. Okay. So look at what's going on here. All the ones with the number on the bottom being, or with the coefficient. Let me start this again. Every term on the right-hand side where the coefficient is positive has an even number at the bottom. All the ones that have a negative in front have an odd number at the bottom. What I'm going to do now, every one with a negative in front, I'm going to move them all to the other side. So the n choose 1 moves over. The n choose 3 moves over. Next is n choose 5, and so on. That's all moved to the left side. And what's left on the right side is n choose 0 plus n choose 2 plus n choose 4, and so on. Now, looking at that, can anybody point out something about the question we're looking at here, about subsets of odd cardinality and subsets of even cardinality and how they relate? So Zhengyi, you're right. The question is about the subsets of odd cardinality, and that is the left-hand side here, right? This is the number of sets. This is the number of subsets of cardinality 1. This is the number of subsets of cardinality 3. This is the number of subsets of cardinality 5, and so on. And Nuran's right is that sum on the left is equal to the sum on the right. And what's the sum on the right? That's the number of subsets of even cardinality. And so what this means is that the number of subsets of odd cardinality is always exactly equal to the number of subsets of even cardinality. That's the result here. That's the important thing to see. Okay. So if that's true, come back to the question now. A set B has 64 subsets of odd cardinality. Okay, if I want to find the cardinality of B, how many subsets in total are there? There are 128 subsets in total. And so I know that 2 to the power of n is equal to 128. And so now it's just a matter of doing exactly what we did earlier. It is a logarithm. It's just a really easy logarithm. So 2 to the 3 is 8. I always have to go back to the bottom. 3 is 8. 4 is 16. 5 is 32. 6 is 64. 7 is 128. So there are 7 elements of B. Hey guys, if you are looking for help with learning discrete math or proofs, I know they're tough, then make sure to subscribe. As I'm literally going to be posting every example I have here for free on YouTube to help you learn and understand discrete math proofs. Back to the example. Justin, no, we just proved that. That's what we proved here. The number of even sets is always equal to the number of even subsets is always equal to the number of odd subsets. Okay, and you can check that out. And this relates to somebody else. Somebody else was asking about a power set. Let's take the set 1, 2, 3. What is the power set of the set 1, 2, 3? The power set is the set of all subsets. So in this case, 1, 2, 3, 3 is odd. So let's see what happens with that. What are the subsets of 1, 2, 3? Well, the empty set, the set 1, the set 2, the set 3, the set 1, 2, the set 1, 3, the set 2, 3, and the set itself, 1, 2, 3. Okay, that is the, yeah, absolutely. That is the power set of the set 1, 2, 3. It's all the subsets. How many have even cardinality? How many have even cardinality? How many have odd cardinality? Well, even, 0 is even. So the empty set counts as even. 1, 2, 3, 4. 4 of them have even cardinality. And 1, 2, 3, 4, including the full set itself, have odd cardinality. Let's just do one more because that might have been a fluke. Doing one with an odd cardinality. Let's do the exact same thing now with an even cardinality set. 1, 2, 3, 4. The power set is the set of all subsets. So we got the empty set, we got the set 1 all the way to the set 4. We got the set 1, 2, we got the set 1, 3, we got the set 1, 4. We got the set 2, 3. We got the set 2, 4. We got the set 3, 4. I think that's it. 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. Yep. We've got the set, and then now the 3 elements. So 1, 2, 3, 1, 2, 4, 1, 3, 4, and 2, 3, 4. And then we've got the whole set, 1, 2, 3, 4. And so I think we might even have a highlighter here. Yeah, there's one. And there's another one. Let's just do it that way for the sake of space on the page. Which ones are even cardinality? Well, 0. There's 1, 2, and 4. So the even cardinality is 1, 2, 3, 4, 5, 6, 7, 8. The odd cardinality, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have 8 of each. We proved it with the binomial theorem. Given any set, the number of subsets of even cardinality is always equal to the number of subsets of odd cardinality. Okay, now that might be a really useful thing to actually write up as a proof. So let's go ahead and try that. Because this is one of the big things you're going to be learning in this class. We're a little early to be talking about proofs, but it's not too bad because it is one of the main things in this class. Use the back of this. So we're going to prove a theorem. Oh, and that reminds me, one thing I would encourage you to do, especially if you're finding any of this confusing or any of this frustrating or strange, is watch the lecture videos of the other profs. We all have our own flavor, our own idea of how to teach this stuff. And so we all teach it in different ways. But we're all teaching the same content. We're all going to be doing the same test. So what that means is that another prof will emphasize something else, another prof will emphasize something else, and because you have access to all the videos, you might find very well that you connect with a different prof's style or a different prof's emphasis. Some of the other profs I know, or one of the other profs at least, has done a bunch of proofs already, and that's the way they like to go about it. So I would definitely feel free to take a look at it and see what you see there. Okay. So the theorem is that for any set A, the number of subsets of A with odd cardinality equals the number of subsets with even cardinality. Okay, proof. Now we can start to see some of the stuff we did in chapter 2 and how this stuff applies. First off, to me, what's most important is actually 2.5, where it does the law of universal generalization. And we talked a bit about that last time, and certainly it's in the video. But the point here is that it says for any set A, this is true. Now, I guess it's implied in this example is finite set. We're not talking about infinite sets here. For any finite set A, the number of subsets of A with odd cardinality equals the number of subsets with even cardinality. So the law of universal generalization says I'm showing something is true for any set at all. Any set at all. It could be a set of colors, it could be a set of people, it could be a set of numbers, polynomials, matrices, whatever the set is, it doesn't matter. Okay. So what do I need to do? Law of universal generality says if you want to show something is always true, you start by saying, let's look at a generic one. Let's look at an arbitrary one and see if I can show it about that. Sound familiar? The idea there is I create one that's arbitrary, a representation of every possible one, and all I know about is the definition of what it means to be that thing, what it means to be a finite set in this case. And then if I can prove it about that, well, then I've proved it about everything. So let A be a finite set. And just by writing that, what I've done is I've now created an arbitrary element that I'm going to prove about A, and then by doing so, I will have proved it about every possible set, because nowhere along the way will I require, oh yeah, A has to have 27 elements, or A has to be a set of cars, or A has to be a set of numbers, or A has to have exactly 32 subsets, or whatever. Like any situation you could require of it, that would not be good, because A is a finite set, and it's just an arbitrary finite set. It might have 1,000 elements, it might have none. It might have 10 billion elements, it might have 5. It might, like, you have no idea anything about it. All it is a finite set. Okay. But whatever the number of elements is, I can name it. Let A be a finite set with, say, n elements. Okay. All right. So now what we're going to do in order to show this is true is I need to bring in the binomial theorem to be able to prove what we just did. Then the number of subsets of A with even cardinality is, and what I'm doing now is I'm going to point out it is n choose how should I write this? I'm just going to write it like this: n choose 0 plus n choose 2 plus n choose 4 plus dot dot dot. And the number of odd cardinality is n choose 1 plus n choose 3 plus n choose 5, and so on, period. Do we need to say that it's a non-empty set? Well, let's check. If A is an empty set, is it true that the number of subsets of even cardinality is equal to the number of subsets of odd cardinality? Well, if A is the empty set, there is only one subset of it. That is the empty set. And that has 0 elements. So there is one even set and there's no odd sets. Interesting. Okay, so I guess I have to throw that out as an option, don't I? Interesting. The empty set is the only set that fails in that example. So we just remove it from the theorem. For any finite set A where A is not the empty set, the number of subsets of A with odd cardinality equals the number of subsets of even cardinality. Good thing to notice, Mark. All right. So now how do I finish this off? By the binomial theorem, capital, with x is -1, y is 1, we get that 0 is -1 plus 1 to the n is the sum, as I goes from 0 to n of n choose I, -1 to the I, 1 to the n minus I, which is n choose 0 minus n choose 1 plus n choose 2 minus n choose 3 plus minus so on. Therefore, move all the negatives over, and we have n choose 1 plus n choose 3 plus dot 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 is equal to n choose 0 plus n choose 2 plus and so on, period. And those are the two things we said were exactly what we were interested in, the number of subsets of the different sizes. Okay. The box at the end, you write a box at the end, that's just indicating the proof is done. Standard way to write the end of the proof. And the point is that the biggest thing to see in this proof is that it's written in complete sentences. Proofs are a lot more like essays than anything else you've done in math. They're a lot more like essays, like it's a lot more like English. And so one of the things that I do warn people in this class about, if you're in this class and English is not your first language, which is usually a very large minority, I'll say a large minority. It's not, I don't think it's quite the majority, but it's a huge chunk of the class. Usually comes in here where English is not their first language. And that's fine, but you actually might have extra difficulty with this class because you are expected to produce English proofs, which involves English grammar, which involves like periods and capitals and sentence structure and all those good things. So do keep that in mind. It's that this is not just, you certainly cannot write proofs in point form. You are expected to actually write these in English sentences. And you might call them mathematical sentences because this sentence here at the end has a ton of math in it, but it ends in a period, right? It's still a sentence. It still has a capital T on the therefore. Like this is a sentence. So things in proofs are way more like essays than anything else you've done. Hey, thanks for watching. Remember, what I've explained here is just a tiny, tiny example in the literally infinite space of problems there could be that you'd run into. So if you're interested in really understanding this content, getting a good grade because you understand the content,
go ahead and click the first link down below and book a free call with me, and let's talk about if I can actually help you do well in this course.